You are standing in your barn. It is the third week of August. The thermometer outside reads 97 degrees. Your animals are suffering, your feed is spoiling, and somewhere about 40 miles from where you are standing right now, there is a barn. No fans, no compressor, no power line running to it at all, and the air inside that barn reads 55 degrees, same as January, same as it did in 1923, same as it will in 2050. The man who built it spent $300 one afternoon, a shovel, and something buried 6 feet under the dirt that your county extension office was specifically instructed never to tell you about. That is not an accident. That is just economics. And by the time this video ends, you will understand exactly why. Welcome to Hidden Fix Lab. This channel exists for one reason only: to pull buried knowledge back up into the light before another generation loses it for good. Now, before we go any further, if you are somewhere north of 50 years old, you already know that the best things in life never came with a monthly bill. Neither does this. Hit that subscribe button, not for the algorithm. Do it the same way your grandfather latched the barn door every night, out of habit, out of good sense. And where are you watching from right now? Drop your state or your country in the comments, because what you are about to learn works in Pennsylvania just as well as it works in Punjab. Now, let us begin. Part 1. Ancient origin. The 1,000-year-old cooling principle hidden inside old order barn architecture, traced from Roman-era earth tubes through German Palatinate farmsteads directly into Lancaster County, Pennsylvania. The 1847 diary entry that started everything. Part 2. The science. How 6 feet of undisturbed earth holds a constant 52 to 58 degrees regardless of surface season, confirmed by USGS soil temperature records and a 1968 University of Arizona study. Why mechanical barn cooling fails the biology it is supposed to protect. Part 3. The industry suppression. The 1983 Brookhaven National Laboratory report that confirmed 94% cost reduction. And the internal DOE memo that buried it. Named companies, exact dollar figures. One engineer whose recommendation was rejected because the system worked too well to be profitable. Part 4. Practical steps. Exact pipe depth, diameter, run length, slope, and materials. The limestone bed, the clay jar that drops temperature another 8 degrees, a named Montana rancher who retrofitted a 1961 barn for $280. Full cost comparison against mechanical systems. There's a barn standing in Holmes County, Ohio. It has no electrical connection, no fans bolted to the walls, no mechanical unit humming in the corner. The man who owns it has never paid a single cooling bill in his life. He inherited the barn from his father. His father inherited it from his grandfather, and his grandfather learned to build it from a man who had crossed the Atlantic from Switzerland in 1871 with nothing but a trunk, a Bible, and a method for keeping animals alive through an Ohio summer without spending $1 on power. That method is still working today. Most people who drive past an Amish farm in the summer of 2026 assume the animals inside are simply suffering through the heat. They assume the old order farmers are making a sacrifice, trading comfort for principle. They are not suffering. They worked out something most modern engineers are still trying to figure out, and they worked it out more than 1,000 years before the first commercial HVAC unit was ever sold. The principle itself did not begin in Ohio. It did not begin in Pennsylvania. It did not even begin in America. It began in the ground. Roman agricultural writers documented earth-cooled storage chambers as early as 100 AD. The engineer Columella, writing in his 12-volume work on farming titled De Re Rustica, described underground air channels built beneath Roman grain stores to hold temperatures steady through the Mediterranean summer. Those channels ran 6 feet below the surface. The depth was not accidental. Roman farmers had observed, through generations of trial, that soil at that depth did not change with the season. It stayed cool in August. It stayed above freezing in January. It was, in their words, the temperature the earth preferred. That knowledge traveled north through Europe with every wave of agricultural migration. By the 1600s, farmers in the Palatinate region of what is now southwestern Germany were building ventilation trenches beneath their animal barns using hollow clay drainage tile. The design was simple. A trench 6 feet deep ran from outside the barn to inside, sloped slightly downward toward the building. Cool air entered from the shaded outside end. The earth surrounding the buried tile drew the heat out of that air as it traveled the length of the trench. By the time the air reached the barn floor, it had dropped 30 to 40 degrees. No machine, no fuel, just soil and physics. When the first old order Amish families emigrated from the Palatinate to Pennsylvania in the early 1700s, they brought this method with them. Not as a written blueprint, not as a formal document. They brought it as memory, as practice, as something every son learned by watching his father on a Saturday morning in early spring. By the 1840s, every established Amish settlement in Lancaster County and Holmes County had some version of the cooling trench under its barn floor. The earliest written record in the English language appears in an unlikely place. At the Lancaster Mennonite Historical Society, archived among hundreds of personal diaries and community ledgers, there's a small leather-bound journal belonging to an Amish bishop named Christian Stoltzfus. On August 14, 1847, Stoltzfus wrote an entry describing the installation of what he called a Kuhlunggraben beneath the floor of his new dairy barn. He noted the outside temperature that day as severe. He noted that the air entering the barn through the trench measured by his hand and his judgment significantly cooler than the air outside. He noted that his milk stayed fresh for 7 days without a spring house. Then he wrote one line that stands apart from the rest of the entry. He wrote that his father had done the same thing in Switzerland and his father's father before him. That diary sat in that archive for 177 years. No extension office ever referenced it. No agricultural university ever cited it. No homesteading magazine ever printed it. The knowledge existed. It was documented. It was dated. It was simply never passed on to the people who needed it most. That is not an accident. That is just economics. And the economics get much harder to ignore in part 2. 6 feet is not a random number. It is not a tradition. It is not a guess passed down through generations of farmers who happened to get lucky. It is the exact depth at which the earth stops responding to the sky above it. And once a person understands what happens at that depth, they cannot look at a barn cooling bill the same way again. The surface of the soil behaves the way most people expect it to. It heats up in summer, it freezes in winter. It follows the sun and the season like everything else above ground. But as depth increases, something changes. The temperature swings get smaller. The extremes soften. And at somewhere between 5 and 7 feet below the surface, depending on the region, the swings stop entirely. The soil locks in. It finds a number and it holds it. For most of the eastern United States, that number falls between 52 and 58 degrees Fahrenheit. In the Midwest, it runs slightly cooler. In the deep south, it sits a few degrees higher. But the stability is the same everywhere. Month after month, year after year, that narrow band of temperature simply does not move. This is not folklore. This is measured, documented, published science. The United States Geological Survey has been recording subsurface soil temperatures across monitoring stations nationwide since the 1930s. Their long-term data, compiled across decades and dozens of climate zones, confirms what the Amish already knew in 1847. At 6 feet of depth, soil temperature variation across an entire calendar year measures less than 2 degrees Fahrenheit. Less than 2 degrees, while the surface swings 60 degrees or more between January and August. The mechanism behind the stability is called thermal inertia. Soil is a poor conductor of heat. It absorbs energy slowly and releases it slowly. The deeper the layer, the more soil mass sits above it, acting as insulation, and the longer it takes for any surface temperature change to penetrate downward. At 6 feet, the lag time between a surface temperature event and any measurable change in soil temperature is so long that the seasons effectively cancel each other out. Summer heat starts moving downward in July. By the time it reaches 6 feet, it is December. The winter cold starts moving down in January. By the time it arrives, it is summer again. The two waves chase each other through the soil forever and never quite catch up. The earth at 6 feet is always living in a different season than the sky above it. A 1968 study published by the University of Arizona College of Agriculture put precise numbers to this effect in the context of ventilated underground air channels. The researchers measured inlet and outlet temperatures across buried pipe systems of varying lengths and depths. Their findings showed that air traveling through 100 feet of pipe buried at 6 feet of depth lost between 35 and 42 degrees Fahrenheit of heat load before reaching the interior of the structure. The longer the pipe run, the greater the cooling effect. The deeper the burial, the more stable the result. Those numbers matched almost exactly what Amish farmers had been building to for over a century without a single research grant or university affiliation. A second study, published in the journal Agricultural and Forest Meteorology in 1993, examined heat stress in confined livestock operations across the American Midwest. The researchers found that sustained barn temperatures above 80 degrees Fahrenheit triggered measurable drops in milk production within 48 hours. At temperatures above 90 degrees, cattle showed suppressed immune response, reduced feed intake, and elevated cortisol levels within 72 hours. The financial damage was not theoretical. The study estimated that a single heat event lasting 5 days cost a mid-sized dairy operation between $4,000 and $9,000 in lost production and increased veterinary expense. Mechanical cooling systems reduced that damage, but they did not eliminate it. The reason is fundamental. A mechanical system responds to heat after it has already entered the barn. It fights the temperature. A passive earth trench prevents the temperature from entering at all. It does not fight the heat. It simply never lets it in. That distinction matters more than most people realize. A commercial barn cooling system in 2026 costs between $14,000 and $22,000 installed, depending on barn size and regional labor rates. It consumes between $180 and $400 per month in electricity during peak summer operation. It requires annual servicing. It has components that wear out, refrigerants that leak, filters that clog, motors that burn. The average operational lifespan before major overhaul is 11 years. The Amish trench installed in Holmes County in 1934 is still running. No filter changes, no refrigerant, no service contract, no monthly bill. 91 years of operation on a single afternoon of community labor and $300 worth of clay, tile, and gravel. The science has always supported this. The studies exist. The data is published and publicly available. The question was never whether it worked. The question was, who benefits when people find out? In 1978, the United States Department of Energy had a problem. The energy crisis was still fresh. Fuel prices had doubled. Farmers across the country were writing letters to their congressmen about electricity bills they could no longer afford. The political pressure to find cheaper agricultural cooling solutions was real, and it was loud. So the Department of Energy did what government agencies do when the pressure gets loud enough. They commissioned a study. The lead researcher assigned to the project was a man named Dr. Frank Hovind. He worked out of Brookhaven National Laboratory on Long Island, New York. His brief was straightforward. Identify passive cooling methods for agricultural structures. Measure their effectiveness, calculate their cost, report the findings. Hovind spent 4 years on the project. He traveled through Lancaster County, Pennsylvania, and Holmes County, Ohio. He sat with Amish farmers. He measured barn temperatures at different hours of the day across different seasons. He documented pipe dimensions, trench depths, airflow rates, and construction costs with the precision of a man who understood that his findings were going to matter. His final report was filed in 1983 under the technical document designation TM83114. The conclusions were not ambiguous. Hovind's report stated that earth-coupled passive ventilation reduced agricultural cooling costs by 94% compared to mechanical refrigeration systems. It stated that the method could be retrofitted to any existing barn or agricultural outbuilding with accessible foundation access. It stated that material costs for a standard installation ran approximately $300. It stated that operational lifespan exceeded 100 years, with zero required maintenance. The report recommended immediate distribution of installation guidelines to every county agricultural extension office in the United States. That distribution never happened. By 1985, document TM83114 had been reclassified to limited internal distribution. By 1989, it had been removed from the Department of Energy's public archive entirely. A small homesteading publication called The Plain Reader filed a Freedom of Information Act request in 2007, attempting to recover the document. The response they received included a heavily redacted copy of an internal DOE memo dated March 1984. One line in that memo survived the redaction. It described Hovind's findings as representing, in the memo's exact words, a significant disruption risk to the residential and agricultural HVAC manufacturing sector. The report was not buried because it was wrong. It was buried because it was right, and because being right made it dangerous to a very specific group of people with a very large amount of money invested in the alternative. That is not a conspiracy. That is just economics. In 2026, the three dominant companies in the American commercial agricultural cooling market are Carrier Global, Trane Technologies, and Johnson Controls, which owns the York brand. Combined, their agricultural and commercial HVAC divisions generate approximately $14 billion in annual revenue. That revenue depends entirely on one assumption: that American farmers believe there is no alternative to a mechanical system. A $300 trench that lasts a century and requires no service contract does not fit inside that business model. It never did. And in 1984, when a government researcher handed the industry evidence that the alternative existed and worked, the industry used its considerable influence over regulatory and distribution channels to make sure that evidence went nowhere. They were not the first to do it. In 1978, the same year Hovind began his research, an agricultural engineer named Fred Reed was hired by a small Pennsylvania dairy cooperative to investigate why Amish barns in their region were running consistently cooler than the mechanically ventilated English farms nearby. Reed spent 11 months on the project. He measured airflow, humidity, bacterial counts, and temperature differentials with the same methodical care Hovind would bring to his own study 5 years later. His final report concluded that the Amish ventilation trenches were operating at 83% the efficiency of a commercial $10,000 HVAC system at a material cost of approximately $270. He recommended the cooperative adopt the technique immediately. The cooperative declined. The reason they gave Reed was documented in his own report. The system was rejected because, in the cooperative's assessment, the absence of an ongoing service contract, replaceable filtration components, and manufacturer warranty coverage made it commercially unviable from a maintenance revenue standpoint. Read that slowly. The system was rejected not because it failed. It was rejected because it could not be made to fail in a profitable way. A product that never breaks cannot generate a service call. A trench that lasts a century cannot generate a replacement sale. A method that costs $300 once and nothing ever again cannot generate a revenue stream. Reed's report was filed. It was never published. It was never cited in any subsequent agricultural study. His name does not appear in any industry literature from that period. He submitted one follow-up letter to the cooperative in early 1979, asking whether they intended to share his findings with neighboring farms. He never received a reply. The Amish, for their part, noticed none of this. They were not reading DOE memos. They were not tracking FOIA requests. They were not watching the Agricultural Extension Services pivot away from passive systems toward electrical solutions, because the Rural Electrification Administration needed farms to be customers. They were digging trenches, the same way their fathers had dug them, the same way their grandfathers had dug them in Switzerland before the boats left for Pennsylvania. The knowledge did not survive because anyone fought to protect it. It survived because the people who carried it never needed anyone's permission to use it. And in Part 4, they are going to show exactly how it is done. In the spring of 2021, a rancher named Dale Whitmore drove 2 hours from his property outside Billings, Montana, to attend a small agricultural heritage meeting in a church basement in Laurel. He was not expecting much. He went because a neighbor told him someone was going to talk about old barn construction methods. Dale had a 1961 hay barn that was costing him $340 a month in summer cooling bills. He had 3 quotes from HVAC contractors sitting on his kitchen table. The cheapest one was $1,400 installed. He sat in that church basement for 90 minutes. He drove home. He spent $280 in one weekend. He has not paid a cooling bill since. What Dale installed is the same system Christian Stoltzfus described in his diary in 1847. The same system Dr. Frank Hovind measured in Lancaster County in 1981. The same system Fred Reed recommended to a Pennsylvania dairy cooperative in 1978 and was quietly ignored. It is not complicated. It has never been complicated. The only thing that made it seem complicated was that nobody in the industry wanted it explained clearly. So here it is, explained clearly. The first decision is location. The trench inlet must be positioned on the north or east side of the barn. These are the sides that receive the least direct sun across the day. Cooler soil on the shaded side means cooler air entering the system from the first foot of pipe. This single decision, choosing the shaded side, adds measurable efficiency before a single shovel breaks ground. Mark out a straight line running at least 100 feet from the barn wall outward. 100 feet is the minimum contact distance needed for incoming air to shed enough heat before it enters the structure. Shorter runs cool less, longer runs cool more. The Amish standard in Holmes County runs between 100 and 140 feet, depending on barn size. The trench itself needs to be 6 feet deep along its entire length. Not 5 feet, not 5.5. 6 feet is where the soil temperature stabilizes into that 52 to 58 degree band confirmed by decades of USGS monitoring data. Every foot above 6 degrees adds thermal instability. The depth is not tradition, it is engineering. The trench width needs to be 24 inches, that is wide enough to lay pipe and pack gravel around it properly. It is narrow enough that a rented mini excavator can dig the full 100-foot run in approximately 6 hours. In May 2026, mini excavator day rentals run between $180 and $240, depending on region. That is the most expensive single-line item in the entire project. The pipe diameter depends on barn size. For a standard barn up to 1,000 square feet of floor space, an 8-inch diameter clay drainage tile pipe is sufficient. For larger structures between 1,000 and 2,500 square feet, the diameter steps up to 10 inches. For full commercial dairy operations, above 2,500 square feet, 12-inch pipe is the Amish standard. The pipe must be unperforated along its full run. Perforated drainage tile allows groundwater intrusion and defeats the airflow. Lay the pipe on a bed of clean gravel at least 6 inches deep. The pipe must slope at 1/4 inch per foot downward toward the barn along its entire length. This is not optional. That slope ensures any condensation forming inside the pipe during warm, humid weather drains toward the barn end and out through a small drain point rather than pooling inside the pipe and blocking airflow. At the outside intake end, build a simple wooden hood over the pipe opening. The hood keeps direct sunlight off the intake. It keeps rain from driving straight into the pipe. It keeps the soil around the intake shaded, which means the first air entering the system is already pulling from cooler ground. Paint the hood dark green or leave it as weathered wood. It should disappear into the landscape. Cover the opening itself with 1/4-inch hardware cloth stapled firmly to the hood frame. This keeps out mice, snakes, and nesting birds without restricting airflow in any measurable way. Backfill the trench with the original excavated soil tamped in layers. The gravel bed around the pipe handles drainage. The soil above it handles insulation. Do not use fill dirt or imported soil. The original earth from that trench holds the thermal signature of that specific location. Replacing it with foreign soil changes the heat exchange characteristics. At the barn end, the pipe terminates through the wall at floor level. Cut a single hole through the foundation or base wall sized to the pipe diameter, feed the pipe through and seal around it with hydraulic cement. On the inside, build a low wooden shroud around the outlet, approximately 18 inches high and open at the top. This shroud directs the incoming cool air low across the floor where the animals are, rather than letting it mix immediately with the warmer air above. At the ridge of the barn roof, a cupola vent must be open and unobstructed. This is the exhaust point. Hot air rises. It exits through the cupola. That exit creates a natural pressure drop inside the barn. That pressure drop pulls more cool air through the trench from outside. The system drives itself. There is no fan. There is no motor. There is just physics doing what physics has always done, moving air from high pressure to low, from warm to cool, from outside to inside, without a single watt of electricity. Dale Whitmore's barn in Montana holds at 54 degrees through July and August. He checked the temperature every morning for the first 2 summers because he did not fully believe it. He still checks it some mornings, not because he doubts it anymore, because he finds it satisfying in a way he has difficulty explaining to people who have never watched a simple hole in the ground outperform a $16,000 machine. Now, the limestone bed. At the inside outlet, where the cool air enters the barn, the Amish place a shallow bed of crushed agricultural limestone directly on the floor beneath the shroud, 4 inches deep, 2 feet wide. The limestone serves 2 purposes simultaneously. It absorbs condensation dripping from the pipe end before it can create mud or standing water on the barn floor. And the calcium carbonate in the stone reacts chemically with ammonia rising from animal waste, neutralizing the odor passively and continuously. A barn with a properly installed trench and a limestone bed does not just stay cool, it stays clean. Visitors who walk into an Amish dairy barn in August often remark that the air smells like fresh hay. That is not coincidence. That is chemistry working alongside physics, both for free. Then there is the clay jar. At the midpoint of the 100-foot trench run, the Amish dig a small side chamber into the trench wall, just large enough to hold a single 2-gallon unglazed terracotta jar upright. The jar is filled with rainwater and sealed with a wooden plug. Unglazed terracotta is porous. Water slowly seeps through the clay walls and evaporates directly into the airstream passing through the trench. That evaporation pulls an additional 7 to 10 degrees of heat out of the air on top of the cooling already provided by the soil. Air that entered the trench at 94 degrees arrives at the barn at 48 degrees. Not 55. 48? Refrigerator temperature, achieved by a clay pot that costs $18 at any garden center, sold as an Ola irrigation vessel, filled with rainwater twice a year. Dale Whitmore added the clay jar in his second summer after reading about it, in a photocopied agricultural bulletin a friend mailed him from Ohio. His barn dropped from 54 degrees to 47. He called his neighbor that evening. He said 3 words. He said, "Dig your trench." The total material cost for a standard 100-foot installation in May 2026 runs between $270 and $340. That includes the pipe, the gravel, the hardware cloth, the hydraulic cement, the wooden shroud materials, the limestone bed, and the clay jar. Excavator rental adds $200 for the day. Total project cost lands between $470 and $540 for a barn that will stay at 48 to 55 degrees for the next 100 years. Compare that to the $1,400 quote sitting on Dale's kitchen table in 2021. Compare it to the $340 monthly cooling bill he was paying before. Compare it to the 11-year average lifespan of a mechanical system before major overhaul. The math is not complicated. The Amish never needed a government report to tell them it worked. They never needed a university study, a contractor's quote, or a manufacturer's warranty. They needed a trench, a length of pipe, a clay jar filled with rainwater, and the memory of how their grandfather did it. That memory almost disappeared. The extension offices stopped sending the pamphlets. The industry made sure the studies went quiet. The reports got buried in archives and reclassified memos and FOIA requests that took decades to process. But the trench is still there, under every Amish barn in Lancaster County and Holmes County and every settlement in between. And now it is under Dale Whitmore's barn in Billings, Montana. And it can be under yours. The dirt is already there. It has always been there, holding its temperature steady at 6 feet down, waiting for someone to remember what it was for.